Okay, so I want to do two things in this video. One is I want to refactor my code just a tiny bit to make it a little more readable, as well as saving a little bit more space. The second thing I want to do is add another directive that's going to be quite useful to save space in certain special cases. So let me re-explain that specific case and what we're going to be adding. So in my particular level, I have a repeating pattern that looks like this. So it's a bunch of repeating strings. So it's a string length of 2 with a tile 1, tile 2, and then it repeats tile 1, tile 2, tile 1, tile 2. So there may be cases where you have repeating strings and not just repeating instances of one tile. So in this specific case, I have 1 instance of the string, 2 instances of the string, 3, 4, 5. What I want to have happen is in the decompiler, you give it a directive. You tell it how many times this string repeats. Sorry. You give it the directive, you give it the length of the string, then you give it how many times that string repeats, and then you give it the string. So this saved half of the data in this particular example, but you can save various bits of sizes of data depending on how long that string is. So that's what we want to add, but first let's refactor my code just a tiny bit. Because I have all of these increment indexes and loading of data, I should have just did this from the start. I should have just called this function load data, which I'm going to do now. So load data. Because every time we load something from data, we're going to have to increment the index anyway for the next time we load data. So I'm just going to put load data here with the index of y, and then right underneath it is where we increment y and account for the overflow. So let's refactor that in. So this decode increment has to stay put, so we're not going to touch that. But here where we loaded the data, let's actually do our function instead. So jump to subroutine, load data. And I can't for the life of me put jump to subroutine down. Okay, jump to subroutine. Now we don't need this increment. This load data turns into load data. We don't need this increment. We don't need this increment. And this turns into load data. We don't need this increment. This turns into load data. This increment goes away. This turns into load data. This increment goes. This increment goes. This turns into load data. This increment goes. And I think that's more readable, and I think this should still work. And it does. So we've saved quite a bit of space because every time we loaded data, we had to increment the index. So that was 2 bytes of instructions. Actually 3 bytes, because the opcode is a byte, and then the address at which the subroutine is located at is 2 bytes. So each time we erased a increment index, we saved 3 bytes. So that was quite a bit of space we just saved there. And it's more readable now. So when we're at fetch, we just load data, we compare it, singles, blah, blah, blah. We transfer to our counter, next action, load data, do something with it, store to tile. I think it's a little more readable this way. Okay, now we want to actually add that exception in. So we go to where we're fetching and comparing. We add in another exception. So we compare with FC. And this is detecting if repeating strings. Then we break if it is equal to a function that we will call strings. Let's write that down here, strings. Now, we're going to need several more things to make this routine happen. It's just a little bit more complicated, but we'll add them as we need them, and I'll explain them as we go. So first, we just load the next piece of data. So load data. And what is this actually loading? So let's look at our format again. We have FC, the directive, which we've already loaded and incremented. Now we're loading the string length. So load length of string. And what do we want to do with that? Let's store this in a variable. I'm just going to call it string length. And we're storing this for later compare. So we made a variable, so we have to add it to RAM. String length. And now we have to load more data. And what is this data? So if we again look back at our format, we have a directive, we have the string length, and then the number of times that the string repeats. So repeat length. Load repeat length. And again, we want to store this into a variable. So this is our repeat counter, we'll call it, repeat counter. Store for later decrement. Okay, so that should be all we need for loading those two pieces of data. Next, we need to read the string and store it somewhere so we can then read it over and over again. So we need to create a buffer. So we're going to initialize our buffer with our string. So we need to load data. And these are tiles. So loading tiles from string. And we want to store that into a buffer. So store into a buffer, and we have to index into this buffer. So let's create the buffer first. And this is going to live in RAM, and we're going to give it a little bit of space. So we're just going to start it at like location C or something. Sorry, location C0. Because I don't expect we're going to be putting a whole lot in this buffer. And I don't think it's going to overflow like a whole page or anything, but we still don't want it to reach the stack at 100. So there's just a little bit of space to store a string rather. So we haven't initialized X for this index, so we want to just make sure that we load X with 0 so we can index into the first location of that buffer. So store into buffer. Next, we want to increment X, because that's our index, and we want to compare the string length. We need to compare X to our string length. Comparing if full string written to buffer. And if it is equal, we exit, but if it's not equal, we continue to initialize the buffer. This is basically the loop. So that should write the entire buffer with our string. Next, we need a loop to read the buffer and to write it to our string. Not string, screen rather. So we have b loop for a buffer loop. We need to initialize x again, because we're then going to read from the buffer back from index 0. Now we're going to load data. Now what are we actually loading? No, don't load data. We've done all that. We have to load from buffer, index x. So this is loading tiles from buffer. What do we want to do with those? We store them to our screen through port 2007, as always. We need to increment our index into the buffer, compare our index with the length of the string, and loop back to b loop until we've reached the end of the string. And we need to do this tiny loop multiple times, and the repeat counter is going to tell us how many times this actually occurs. So we want to decrement our repeat counter. Now to compare something in RAM, we actually have to load it because it's not in any register. We've just decremented a number somewhere. So we load repeat counter, and then we break if it is not equal back up to the loop, because we've stored a value that we're going to decrement until 0 happens, and when it actually reaches 0, we break out of this loop. So after this loop is broken, though, we need to reinitialize x, because we're reading this buffer multiple times, and we're using x to index into the 0 position, the 1 position, the 2 position. So we have to initialize that every single time we restart this tinier loop. So that's why we're initializing x here. No, I don't do it there. That's the wrong spot. So I need to do it right after this loop. Yes, right after this loop, because the first time we break out of this loop is after the string length has been met. Then we reinitialize x, decrement our repeat counter, and if we have not hit 0, we just start back up the buffer again. So this has to be initialized here. And then after we break through here, we jump back up to fetch. Okay. So I think this should work. Let's actually compress our data. So I'm going to open up level.rle. So I haven't figured out how to actually compress this automatically yet, but this is going to be easy enough. So we have a repeating pattern. Let me do this in a text editor so it's more visible. So we have a repeating pattern of 01, 02. We have this 256 tiles in a row. So since it's a string length of 2 and there's 256 tiles in total, we want to divide 256 by 2, and that's going to give us our repeat length. So we go to a calculator, we put in 256 in decimal, we divide it by 2, this equals 128. Convert this to hexadecimal, that's 80. So 80 is going to be our length. So let's just take this whole string of 256 tiles, erase it, put in our directive FC, our string length of 2, our repeat length of 80, and our string of 0102. We're going to hit save. As you can see, this is very, very compressed. This is almost no data at all, but this should be our entire level now. So let's take RLE, let's move it over, let's copy and replace, and let's actually try to run this, and hopefully it's the moment of truth. Unknown label. So 109, 138, 154. Okay, so let's go to 109. I probably changed something I shouldn't have. 109 is called strings. Oh, and I named it stings. So strings. What is 138? Let's go to 138. Repeat counter. Did we not put this in RAM? We did not. So repeat counter needs to go in RAM. And I bet that's what those other errors are. So let's just run this. So no errors. And we have our screen. So we have successfully, let me get both of these out real quick. We've turned this huge name table, which is a kilobyte in length, into this. So this is about 33 bytes long. 33 bytes just houses all the information we need for this 1 kilobytes worth of screen data. And we've successfully decoded it. I'm going to be working on how to do this automatically in my compressor. It's just a lot more difficult to figure out sorting the data out and writing it in a compressed manner than it is on just reading the raw data and unpacking that information. So hopefully I can figure that out. Otherwise, I don't really mind hand compressing it when I've already done a few levels of compression already and it's just a single screen. It's not too bad. We only had to do one instance of it. There may be a few, but it's not too bad even if I can't figure out the automatic compression part of it. But glad we got that working, and that just goes to show how much compression you can actually implement on certain types of screens. Thanks for watching.